Hello, in this video we're going to look at how we can change the behaviour of a program after we've compiled and released it. And I'm going to do this by looking at using an external scripting language to augment the functionality of our original program. In this case I'm going to be using Lua because I like Lua. It integrates with C++ very well, and it's a very quick language, and it's also syntactically quite simple. The practice of using scripts to augment our programs is getting more and more common, particularly in the gaming world, where modification of games is actually becoming a business in its own right. It's also very useful for businesses and industry to be able to modify their programs rapidly without needing to recompile the original source or get hold of the original developers. So I'm going to take a very quick look at how we can get Lua and C++ talking to each other. But I should point out that this video is not intended to be a Lua tutorial. I believe Lua is syntactically simple enough that if you've got even the most basic programming knowledge, you'll be able to look at some Lua code and understand its purpose. I'm going to start with an empty C++ program. It's just an int main. But so I don't have to answer the same question 1,000 times over, I'm just going to quickly show how we get hold of Lua and set it up. Firstly, go to the lua.org website. This is the home of all things Lua, and click the download button. Now, you can download the entire source for Lua, but I'm not going to do that. Instead, what I suggest is you go to binary, and you download the binaries instead. What we don't want to do is compile all of the source. If you're on Linux, you might want to do that, but I don't. And then click on the latest version of Lua, so in this case it's 5.3.5. and go and download what you need. So in my case it's Windows Library. I'm going to download the dynamic version of Lua, so it's going to be loaded in as a DLL, and I'm going to choose the 32-bit version, which is this top one here. And here is the zip file I've just downloaded. It contains a static library, a dynamic library, and an include folder with some header files in. At this point I should probably mention that I'm showing you how to do things the way I do it, which might not necessarily be the best way. In fact, when it comes to embedding external languages, there are many ways to achieve the same thing. How you come to that decision depends on the application that you're building and how you intend it to be used. Since Lua is so small, I like to include a local copy of it in my C++ project. On the right here I have my Visual Studio solution, so I'm going to create a new folder in here, and I'm going to call it Lua 535, which represents the version we've just downloaded, and into that folder I'm going to copy the contents of the zip file. I'm then going to take a copy of the DLL file and paste it directly into the project folder. And as I've just mentioned, there are 1,000,001 ways of achieving the same result. Particularly on Linux, you may want to install Lua to a known location and always reference that one instance of Lua. Lua is fundamentally a C library, so I need to tell the compiler that I'm going to be dealing with C-defined functions. I do that using the extern keyword. And then I'm going to include the Lua header files that I need directly referenced to the local Lua 535 path of the Visual Studio project. After we've included the header files, we need to link to the library. Now in Windows and Visual Studio I can use a hash pragma for this. There'll be lots of people complaining about that because not all compilers support it, so I'm guarding it with Win32. This approach saves me from having to alter any of the project properties directly. Depending on the building toolchain that you're using, you may need to include additional directives to the compiler to link to this library. And that's it, that's all we need to start using Lua. One of the nice things about Lua is it doesn't really get compiled until you need it. So it always exists in a nice text form, and this is perfect for modification because it allows other people to edit that text in an understandable way. Let's start with a very simple example to demonstrate what I mean. I'm going to create a standard string called command, and I'm going to define something in that command. A equals 7 plus 11. The goal here is to get Lua to execute this expression and return the result. To do anything with Lua, you need to create a Lua state. Now, the function syntax for interfacing with Lua is a little bit old school and wordy, but actually using Lua is quite simple and intuitive. And Lua convention dictates that a single capital L represents a single instance of a Lua virtual machine. So here I have created that Lua virtual machine. I'm now going to tell that instance of the virtual machine to do something, and it'll return an error code whether it could do it or not. In the simplest possible way, I'm going to tell Lua to simply execute that string with the doString command. I pass in an instance of the Lua virtual machine, and I'm also going to pass in my string. Now, because this is a C function, standard string doesn't really apply, so I need to actually get that as a character buffer using the cstr method. And now we've reached the first and most important lesson when embedding any external scripting language. You must validate what's happening, because you've got ultimately no control of what the end user might have scripted. The script could contain syntax errors, it could contain malicious code, it could contain code that locks up and freezes your program. And there are other things too, regarding the information transferred from the C++ domain to the scripting language domain, and we'll look at that in a bit more detail later. So the first thing I'm going to do is make sure that that string executed successfully by checking the value that was returned. In this case, we can check to see if R was equal to Lua OK. If it wasn't OK, I'm going to interrogate the virtual machine about the nature of the problem. And to do that, I'm going to interrogate the Lua stack. And I will go through what the Lua stack is in a minute, but right now, just stay with me. Assuming the script did execute successfully, we want to get the value A from our command. Well, in this case, A exists globally within the Lua virtual machine. So I'm going to use the Lua getGlobal function to give me access to the variable A. And herein lies another round of validation. I don't know what type A is. Lua fundamentally is reasonably typeless. This is very different to C++, where everything is quite explicitly defined what it is and how it's stored in memory. Now, I am expecting the result A to be a number, and so I'm going to test explicitly, is it a number? And again, we see this strange notation, and I will describe what that is in a minute. Knowing that A is now definitely a number, I can reasonably safely convert it to a C++ float. So here I've created a variable A in C++, and I've used the Lua toNumber command to convert whatever A was into a number, and I'm casting it to a float. I'm now just going to output that value to the console. Now there's a further little bit of housekeeping to do before people start writing in and complaining. Whenever we've created a Lua virtual machine, we should also clean it up. We can use the Lua close function to do that. And this will make people really angry. I'm also going to throw in a system pause, just because it makes making the video a bit easier. So here we've got a simple program. We take a command, a equals 7 plus 11, we create a Lua virtual machine, and we tell it to execute that command. We then check, did it successfully execute the command, and if it did, we try and extract the value A as a number, so we can display it in C++. If it didn't successfully execute the command, then I'm going to display any error messages that the Lua virtual machine has returned. So let's take a quick look. Well, we can see that Lua was successful in that it added 7 and 11 and gave us the result 18. But let's see how helpful Lua can be by adding a syntax error to our command. In fact, it even returns. On line 1 of our command, the number was malformed. So, what's this all about then? Lua and C++ talk to each other via a stack. And if you remember, a stack is a first in, last out data structure. So as data gets put in, it starts filling up the box. And in principle, you can only take data out of the box if it was the last item put in it. However, the Lua stack does kind of break this rule, as it allows us to index individual elements within the stack's buffer. And this is quite an elegant solution to a particular problem. As I've already mentioned, A in Lua could be anything. We've not declared a type for it. A is simply some object with a value. And this presents C++ with a problem, because it likes everything organised and defined. So I want us to conceptually envisage that each element on this stack is actually a box that contains some data and a description of how that data might be interpreted. And so when we call functions like Lua isNumber, what we are doing is asking the box to test its contents to see if it can be interpreted as a number. When we called the Lua getGlobal function, and if you remember, we passed to it the Lua virtual machine and our variable. an interesting transaction occurred. Into the stack we put the variable a. Lua then went away and popped a off the stack and pushed onto the stack the box that it has that defines what a is. And in this case, a is also associated with a value, 18. The Lua stack can be indexed in two ways. One is explicitly, starting at 1, oddly. So 1, 2, 3, 4, 5, 6, which implies that 0 is an empty stack. However, Lua also provides a second way to index a stack, and you can index it relative to the top of the stack. So the top is -1, the next one down is -2, -3, -4, -5, etc, etc, etc. This is a convenient notation to make sure you're always working with data near the top of the stack, which is likely given the functions that you've been calling. No doubt this does take a bit of getting used to, and we'll see it does become reasonably complicated when you start exchanging more sophisticated data structures. But what is quite nice is it is always deterministic, so you can always work out where you are on the stack. So looking at our getGlobal function, we can see that we're effectively pushing the name of a box, A, onto our stack. Lua then looks for a box named A and replaces it on the stack with the contents of that box. We know that the -1 index is going to be the top of the stack. So I can interrogate that location on the stack to see, can that box be interpreted as a number? Well, in this case it can, because it contains the value 18. Since it can be interpreted as a number, I then ask Lua to go and directly convert its contents of that box to a number that C++ can understand. When we put the syntax error into the command, it didn't know how to execute the command, and it placed an error message as a string on the top of the stack. I wouldn't blame you for thinking, well, so what, this all seems like a lot of effort to add 7 to 11. But Lua is actually quite a powerful and well supported language, so we can use more complicated functions within the framework. So let's say I wanted to take the sign function of some value. Let's see what happens this time. Oh, well, we've got a syntax error, attempted to index a nil value. It doesn't have any representation for what math was in that command. Well, math is in fact one of many Lua libraries, but we need to tell our Lua machine which libraries it can have access to, because don't forget, being safe when you're running people's code and you don't know what they've written is very important. Explicitly listing all of the libraries by hand can be quite tedious, so Lua thankfully provides the function Lua openlibs, which opens sort of the basic set of libraries that most programs will use. This has now added math to the virtual machine, so let's try it again. And we see this time it's quite happy to compute it, and we end up with, well, whatever the result is. The standard libraries in Lua provide all of the basic things that you might expect a programming language to provide, including things such as file handling and operating system manipulation. But since Lua has a robust community around it, many other third-party libraries are also available that can do pretty much anything and everything you need it to do. Since I'm going to be checking the status of the Lua virtual machine quite frequently, I'm going to create a little utility function to help do that. It just checks for an error message, which means I can simplify my program. I think it's important at this point to demonstrate that the Lua virtual machine is persistent, so any changes to it last between calls. So in the first command we executed this maths expression, but let's say on the second command I want to use the result from the first one, so a equals a plus 100 for example. I'm then going to reuse the code I've created to execute the next line. So we can see the first time we got the original result, and then we got the same result at plus 100, with a little bit of floating point rounding. And this implies that we can sequence instructions to the Lua virtual machine, which makes sense. It is, after all, a fully functional programming language in its own right. But it also means that we could construct these instruction commands as necessary in our C++ code. But let's be honest, doing things line by line sucks. What we actually want to run is a Lua script. I'm going to add a new text file to my program, and I'm going to save it as, in this case, it's going to be video example.lua. Then I'm going to add that text file, videoexample.lua. Still got the text at the end of it, let's get rid of that. I'm going to add that to my Visual Studio workspace. Now, nicely, Visual Studio can syntax highlight Lua, so things get a bit simpler to read. So I've got what is a Lua script. And a Lua script is quite an important concept, because here the strings are still hard-coded within the C++ program. But if we now externalize them as a script, other people can edit them, and our program will run them. Let's test this by taking our two silly commands and adding them to the script. We'll save that. I'm going to go back to the C++ program, and I'm going to delete this second half. And instead of the doString command, I'm going to call the doFile command. And instead of the command as a string, what it's expecting is a file name. videoexample.lua. We no longer need the command, we can get rid of that. So now Lua will load this file and execute all of it. Let's take a look. Well, no surprises, we get exactly the same result as we did before. But without needing to recompile the program, I can change the nature of the script. And rerun, and you see Visual Studio didn't even compile, it just ran the Lua script, which is perfectly fine. That's exactly what we want. And this framework allows us to do our first simple thing with Lua, and that's just use a Lua script as a settings file for your application. So I'm going to define some values in my Lua script, which I'm going to import into my C++ program. We can see in these settings there's some common linkage. They all look like they define a player. So in my C++ program I'm going to create a struct which represents a player. And we'll create a single object, player. We've seen already how to interrogate global values in a Lua script. This time, instead of looking for the variable a, I'm looking for the string, and I'm expecting it to be a string, and that's an important thing, is string. And instead of returning a floating point this time, I'm going to convert to string. So this feeds into what I was saying earlier. It's very important that you know what the nature of the data you are expecting is. I've modified the code here to simply display the player's name. Kieran, excellent. Now, a naive approach is to duplicate this for all of the different fields. So I've just modified the program to read in all of those settings. And we see Squire Kieran of Wirral level 20. And I don't think I even need to demonstrate that if I change these settings, the string will change in the C++ program. So using Lua as simply a configuration file for something is quite simple, but it did seem a little involved. There's a lot of effort to go to there just to extract the data that you're looking for. Now, that's because of how we've structured the settings in Lua itself. Since we've got Lua available to us, we may as well leverage its abilities to handle information for us. So instead of defining all of the properties of a player object individually, let's actually create a player object. And Lua being Lua, there's several ways to go about doing this. So a simple one is using key and value pairs. So let's give it the key title and give it the value. What we have here starts to demonstrate the power of Lua. We've effectively created a box called title and given the box contents of Squire, and we've put that box in an overall box called player. Lua has additional ways of reaching the same goal. So let's have a look how we interrogate this global object player to get the contents. And I'll just comment these out. Well, starting at the top of our C++ code, we know that player name is no longer what we're looking for. What we're looking for is a global object called player. Now, player, as we defined it, is no longer a simple type. It's actually a table. containing names and values. So I'm going to make sure that the global that is found is in fact a table. And just to keep things clear, I'm going to remove the previous code. To find a particular element in a table, we need to add the name of that element to the Lua stack. So I'm going to use the Lua push string command to do just that. And what's important to note is that the location of the table has now changed. Whereas -1 indicated it was at the top of the stack, now at the top of the stack is the string name. The table will be at -2. A call to the Lua get table command, don't forget it's at -2, will look at the top parameter of the stack, find the relevant key value per, pop the name off the top of the stack, and replace it with the value that we're looking for. So the top of the stack now contains the value of the key that we were searching for. However, our stack is now not arranged the way we think it might be, so we need to maintain our stack by popping the top element off. Maybe some OneNotes in order here. After the first call to get global, we know that the object player was placed at the top of our stack. Remember that these things on the stack are essentially boxes with a name, so this box contains a table. So I used the Lua is table command on the top of the stack to verify that. And indeed, it is a table. It is an object that consists of other things. Those other things are keys and values. And not to confuse things too much, but these values could be other tables. But I'm leaving that well alone for the time being. The top of our stack was denoted as -1. I want to search my table for a specific key value per. In this case, I want to use the key name to try and find the value Kieran. So I need to issue the key to the Lua virtual machine, and I do that by pushing it onto the stack. This has now changed the indices, because -1 is always the top of our stack, and -2 becomes the location where the table existed. I then call the Lua get table command, being careful to make sure that I choose the right slot on the stack. This command uses the value at the top of the stack, in this case it's the string name. It pops that off and uses it to return the appropriate value. Once the get table command has successfully executed, I then call Lua toString on -1, the top of the stack, to ultimately get the value that I'm interested in. But now I'm left with a value at the top of my stack that I no longer want. So it's important to pop that off the stack, resetting the stack to how it was at the start. If I choose not to pop the value off the stack, I can still do things. I just have to maintain the indices properly. This can get quite complicated when working with large structures and structures with nested structures. So I find it's always better to maintain your stack at the micro level rather than the macro level. This means I can cut and paste the same code now to get the other elements of the structure I'm looking for. And you may notice I can also do things out of order because I'm doing a key value search each time. The odd one out is of course level. Even though the key is a string, the value we're expecting is an integer. Just before I run it, a quick reminder of what the original script looks like, and I'll click play, and of course we see the result that we expect. So far we've looked at very simple methods to extract information from a Lua file, and they can get a lot more complicated than what I've shown here. Again, it depends on your application and how you're approaching the solution to your problem. But what we really want to do with external scripting languages is get them to solve problems for us. i.e., it would be good to be able to call functions in Lua from our C++ program. So let's have a look at just that. For now, I'm going to comment out this code because I want to reuse it later. I'm going to go back to my Lua script, and I can leave that there. I'm going to create a function. I'm going to call it addStuff. And the function is just going to take two variables. So we're just going to simply add them together and return the result. My variables are going to be A and B. Of course, a function must return something, so I'm just simply going to return A plus B. But I'm also going to add in a little utility to help us keep track of where we're up to. You don't need to do this, but it makes the video a little bit more visually interesting. I'm going to use the print command to inform me that Lua has indeed been called. So I'm going to have a little square bracket with Lua in it, and a note that the addStuff function has been called. In fact, I'm also going to put in the parameter values. The two little dots basically concatenates things together. The Lua print command will output to standard out. That's the same console that I'm using in my C++ program. Calling a Lua function is actually quite easy, but I will stress that from this point on in the video I'm not going to include all of the necessary error checking, just to keep things a little bit clearer. The function, just like any variable, is just defined as a box with something in it. In this case it contains a function. So it's important that we first of all get that box and put it on our Lua stack. I will test to make sure that what is in that box can be interpreted as a function. If it can, I'm going to push two things onto the stack. I'm going to push two numbers just directly, 3.5 and 7.1. That's going to be our A and B arguments. I'm now going to use a new function, Lua pcall, and this takes the arguments of the Lua stack, how many arguments we're providing, in this case the 2, how many arguments we're expecting in return. And the final argument is a little bit more advanced. That's actually used to define how our errors handled within the Lua script, and we might look at that in a later part in this series. So in a similar way that the doFile function has executed the whole script, the pcall function has just executed the single function with the arguments that we've provided. If that is all executed okay, then we need to look at the result that's been returned. Because we have told Lua that the function is expecting 2 arguments, it will have popped those off the stack in order to use them. So we know that the top of our Lua stack will reflect the returned result of the function we've just called. So I'm going to put quite a verbose message in here. C++ called in Lua the addStuff function with those parameters, and in return, and here we use the Lua2number function to turn whatever is at the top of the stack to a number, and we'll display it. So let's take a look. Well, we can see that Lua first outputted with the print command the 2 parameters that we passed in, albeit with some floating point rounding. And then our C program got the result 10.6, which is correct, and displays that. So here we've offloaded a task to Lua to go and solve. Of course, the C program, once compiled, isn't easily modifiable, but the Lua function certainly is. So instead of adding stuff, let's multiply stuff. Straight away, no compile needed, the result is different. You could even go as far to make your C program sensitive to this text file changing. Although that's quite an advanced thing to do, we might leave that also for a later video. Now we can call functions in Lua. We can lean on Lua to start doing more complicated things. So let's have a getPlayer function into which we pass an index. I've modified the Lua script to contain a small database of the players and added a getPlayer function to return the player at a specific index. In the C++ code, I'm going to modify it to now find the getPlayer function, and I'm going to push a specific argument, in this case 0, the player at the 0th location. I'm only going to call the function with 1 argument, and I'm only expecting 1 result, the player object. I'm now going to borrow the code I wrote before. So this time, depending on the argument that I provide to Lua when calling the getPlayer function, it will choose the appropriate player from its array of players. Let's see what happens. So as before, we see Squire Kieran of Wirral, level 20. But if I change the code to now find the other player, so I'm just changing the argument, we get Lord Diego of Brazil. The Lua script is now making decisions for us. So though we've looked at C++ calling Lua functions, a very flexible and powerful thing to be able to do, because don't forget Lua is a complete programming language. It can have its own loops, its own decision making, its own access to system libraries, it can do whatever it needs to do. But sometimes Lua may need to call functions of the host environment, the C++ environment in this case. So let's take a look at that. I'm going to create an additional Lua function. I'm going to call it doAthing. And it's going to take 2 parameters A and B, so I can reuse a little bit of the code I've got already. And as before, I'm going to make it print out the fact that it's been called, just so we can keep track. But then I want it to call a function in the C++ environment. I don't have a name for this function yet, but I'm just going to create a variable C, and I'm going to call it host function, to which I'm going to pass in the parameters A and B. So it does seem a little bit redundant that we're creating arguments A and B in the C program, passing them to Lua. Lua then passes them back to the C program, but this is just going to demonstrate the transactions that are required. In fact, you know what? Let's just modify those slightly in the Lua environment so we know that they're slightly different parameters. I then want my Lua function to return the computed value. I'm going to modify the C++ file to call the doAthing function. And as we did before, I'm going to push two numbers, 5 and 6, and call the function. I'm going to get rid of the code displaying the players. So right now, let's just call the doAthing function and see what happens. Well, we can see that doAthing was called, but then we got an error at line 34, attempt to call a nil value, global host function. Of course, we've not defined what host function is. And that error, don't forget, was caught by a little utility function, checkLua, that we created at the start. So we need to tell the Lua virtual machine what host function is. And when creating a function in C++ that is callable by Lua, it has to follow a specific definition. It is the function name. I always prefix it with a little Lua, so I know that they're different. I'm just going to call it host function. And it takes a single argument, which is the Lua state. What this function returns isn't the result of anything, it's the number of arguments that will be passed back to Lua. So in this case, the argument is just going to be 1, the value, which will ultimately be passed to C. Don't forget, of course, we don't have to pass simple values. We can also pass complex table structures as well. So let's do something in this function. I'm going to get the values A and B that are on the Lua stack that has been provided to us. But you'll notice something different. I'm not indexing them -1 and -2. The way I interpret this is I've got a fresh stack to play with, and it's already pushed onto that stack the two arguments that it's calling. These two. And it's probably good practice to make sure that the number of arguments you are expecting has actually been returned. And you can do that with the Lua getTop function, which will return how many elements are in the stack. I've not done that here, just to keep things a bit clear. What I will add to this is a little output, just so we can keep track of where things are up to. So we can see host function has been called, and then I'm going to calculate the result. In this case, a simple multiply. I then want to push back onto the Lua stack the result with the Lua push number function. And as I mentioned earlier, I'm only pushing one thing onto the stack, so that's the value that I'm returning, 1. So this is great. We've now defined a function in C++. We need to link it to the virtual machine. And Lua very conveniently provides a routine for us to do that. Lua register. And in it I provide a string name, so that's what Lua will actually use to call the function, and I provide a function pointer to the function that we've defined. And that's all we need to do. So in the area where we've called the original doAthing function, let's display what the ultimate result is and see if all of this works. So the first thing that's happened is the doAthing function in Lua was called, with the values 5 and 6. That function then went on to call host function with the values 15 and 18, and that's because that's what we've described in our Lua script to do. We added 10 to the 5 and we times the 6 by 3. The host function in the C++ environment simply multiplied its two arguments together, and 15 multiplied by 18 is 270. The Lua function simply returned that result back to us. So the C environment ultimately sees the 270 value again. Yes, a little bit redundant, but we've covered sort of all use cases here of transaction between C++ and Lua.
And so that's that. We've really only taken a very scratch the surface look at interfacing Lua and C++. And what we've seen is it's actually not the most trivial thing in the world, but it does get simpler as you get more acquainted with how the Lua stack operates. Being able to enhance your program's functionality is a really cool thing to do, certainly when you can start creating games and applications that can be modified by other people. And that's exactly why I wanted to include this video before going to the next part of my top-down city-based car crime games series, because I am actually going to be using Lua to handle game settings and mission-based operations in that application. But you may have noticed that this video is also tagged with the ominous #1, implying that it's part of a larger series. And I think it will be, though I don't know what the schedule will be, because there's a lot more cool stuff you can do with Lua and C++. Anyway, I've put some code on the GitHub for this. It's not quite exactly the same as what we've seen in the video, simply because it doesn't really make much sense on its own. So I've tried to write an annotated form which covers all of the basic transactions between the two different environments. So have a play with that and let me know on the Discord if you have any difficulty getting it set up. If you've enjoyed this video, give me a big thumbs up, have a think about subscribing, and I'll see you next time. Take care.